Good morning. So I'm Dr.S.J.Mohan, Professor of Civil Engineering, Bharat Institute of Higher Education Research, Chennai. So today my topic, good morning, welcome to all. This is our third lecture on the subject of structures on expansive soils. Code is Bce078 and we are continuing with the third lecture on the same unit. On this topic, what we are going to talk today's lecture is on heaving of soil. I'll just explain what is heaving of soil, then we'll go into the depth of what does it mean by heaving of soil, and then what its implications on foundations all. We will see one by one. Heaving of soil means the upward movement of the ground, usually associated with the expansion of the clayey soil, which swell when wet. As the soil generally cannot expand downwards or sideways, the result is that exposed upper surface of the soil rises up in its level. With the result, the soil swells abnormally, which causes damage to the foundations. So this we call it as a heaving of soil. There are different types of heaving. The shrinkable clays or soil containing a large portions of mineral particles of less than 0.002 mm in diameter. This produces an extremely cohesive soil type when wet, but shrinks to a crumbly, crashed, and structure when dry. The expansion and contraction process during wet and dry period is known as clay heave. The ground heave often occurs when a mature tree near the property is removed or dies. Once the tree is removed, this water will rehydrated on subsoil and cause it to expand because the soil used by the tree is not being used right now. With the result, the soil swells, causes damage to the foundations. So these are all different types of the heave. Heave prediction. How do you predict the heave? What will happen when the structure is constructed on the heaving soil? How the expansion of the soil can take place and what is its implications on foundations? So these things can be identified if you know how to predict the heave. The reasonable estimates of anticipated vertical and horizontal heave and differential heave are necessary for the following applications. What are the applications are? Determination of adequate design of structures that will accommodate the differential soil movement without undue distresses. Of course, the undue distresses means it is expected no cracks can happen or visual cracks could be seen on the structures. So these predictions are also needed to estimate the upward drag from the swelling soil on portions of deep foundations. So determination of the technique to stabilize the foundation and to reduce the anticipated heaves. So that's how the heave prediction become essentially needed then. The factors influencing heave are the difficulty of predicting the potential heave is complicated beyond these factors by effect of the type, the geometry of foundation, depth of footing, and distribution of load exerted by footing on the magnitude of the swelling expansive foundation soil. So these are all some of the factors which severely influence the heave factors of the soil. The additional problems include estimating the exact location that swelling soil will have or the point source of the water seeping into the swelling soil, the final or equilibrium moisture profile in the area of the heaving soil. The heaving soil in generally, if you want to know, it's all fine grained soil which are of a varying type of the fine grained soil like a clay soil or a peat or a black cotton soil. This will swell abnormally when the moisture content increases. Because when the moisture content increases, the increase in the volume could not be accommodated below the earth level. It expand on the surface of the soil, so it push up the structure which is standing on that, causes some undue damages and cracks in the building. That you call it as heaving of the soil. And this can happen when there is a tree is being cut, or when the moisture is being lost, or when the moisture is being extra added. Then you will feel that the heaving of the soil have an effect on the structures. The method of heave prediction. How you can predict the heave predictions can be done. Or there are two methods, 2 to 3 methods are there. We cover broadly 1 or 2 methods here. Basically, they are all empirical methods. The foundation soil may expand both vertically and laterally. The vertical movement is usually of primary interest. So the vertical movement we are very much interested than the lateral movement, which can be accommodated by the structure. For it is the differential vertical movement that causes most damages to the overlying structure. As I said earlier, the vertical deformation of the soil or swelling of the soil straight away having an effect or impact on the structure on which it's sitting on that, with a result the structure affect very badly in that. So that we are very much interested. So the vertical heaving we are very much interested, that you call it as sometime the heave potential of the soil. Methods of heave predictions. The vertical movement. The methodology for the prediction of the potential total vertical heave requires an assumption of the amount of volume changes that occurs in the vertical direction. The fraction of volumetric swell, or the N, that occurs as heave in the vertical direction depends on the soil fabric and anisotropy. The anisotropy, what do you mean by is, there can be a differential expansion or differential swelling is possible in the soil. So if it is a vertical direction, it may be more, lateral direction it may be more, or sometimes it may be vice versa. You call it as anisotropy. The vertical heave of the intact soil with a few fissures may account for all of the volumetric swell, such as that n is equal to 1. While vertical heave of the heavy fissured and isotropic soil without the horizontal restraints on the soil swells that exist in the field, and during one-dimensional consolidation swell test can predict the heave very nearly to the accuracy. So the consolidometer, what you use for the heave prediction, is also termed as OEDOMETER. OEDOMETer is used for to predict the swell of the soil. Let us see how this is being predicted using the OEDOMETer. An OEDOMETer is is a prediction to find out the vertical swell of the soil. So the soil which required to understand should be kept in a ring specimen. So what you call it as the test sample, this is a ring. So this is in the form of a ring. Inside the ring, the test sample is kept. Then a load is applied, a calculated load is applied so that the soil is under the stress. This simulates the foundation stress on the soil. It is just to simulate the foundation load on the soil. Now, the loaded soil is supplied with the water or the moisture content, so that the moisture content goes on increases and swell increases. When the swell increases, there is an increase in the elongation along the vertical direction. The increase in the vertical elongation by the original length, you call it as the strain in the soil. So there is a stress in the soil, there is a strain in the soil, there is a water content in the soil. All these three parameters are measured or being measured in the OEDOMETer. This is another form of simplest form of the OEDOMETer. This is an expensive form where the moisture content can be controlled here. Here you just send the moisture control through a porous media, and porous media control the pressure of the oil or pressure of the soil, water content, and then this is taken out by a drain pipe from the porous media. That is how the drainage path or the drainage is being controlled in the test specimen. The height of the soil may be 20 mm or maybe 17 mm sometimes. So these two thicknesses are being tested in the OEDOMETER to find out the heave in the soil. The OEDOMETER test and the heave prediction. The numerous numerical methods have been developed for the estimation of the heave, swell in the vertical direction. But few of these methods have been validated experimentally, and there is a limited amount of experience regarding the reliability of the available prediction methods. Yes, though there are a lot of the empirical methods are being adopted, but the reliability will be very limited for certain items only. Certain values of the certain procedural usage of the certain procedural usage of the equipments only have the reliable, and those one or two methods we are presenting here for the OEDOMETER test to predict the heave. The popular test in measuring the swell potential and swelling pressure or testing equipment is commonly available in most soil mechanics laboratories. The simplicity of its operation, most geotechnical engineers are familiar with the testing methods because it is very similar to your consolidometer. Consolidometer is used for find out the initial settlement and final settlement of the soil. It is very nearly equal to that, and it is called as OEDOMETer because it is used for predicting the heave of the soil, not exactly the consolidation. The heave prediction method, the Moore et al. Method. Et al. Means there are other authors' work is also involved in that. Moore et al. Proposed a practical method to predict the vertical movement heave of the soil based on change in with water content. A simple method for predicting the vertical strain, epsilon V is a vertical strain, as a function of change in the water content del W at a given total applied vertical stress of sigma V was proposed. So for a sigma V, see where the delta H can be found, which is a ground surface movement, which is equal to H naught, the thickness of the soil layer, del W, change in the water content, then CEW is the slope of the swelling line. The slope of the swelling line, you get it from the OEDOMETer. Let us go into the depth of the subject, how to find out the slope of the swelling line. Because that is one of the component used in the Moore et al. Method. Along with that, you use the ground surface movement and thickness of the soil layer, then change in the water content to predict the delta H, that is the ground surface movement. Let us go into the CEW, which is precisely stated here as CH. It is a slope. That slope, you can get it when there is a vertical strain if you can measure for a given change in the stress. For example, sigma 1 prime, sigma 1 2 prime, sigma 1 2 prime, sigma 2 2 prime. Then if there is a change in that and there is a change in the strain here for a given value of the water content, then this line represents the slope of this line represents CH, which is also equal to epsilon of CEW or something which we have seen it in the previous lecture. That formula, if you are interested, see epsilon W. It is not E, it is epsilon W. So that is the slope of the line CH. It is given in the different rotations. So there is an applied stress and there is a vertical strain. Any two difference between these two things will give the slope of that line, and that you measure it as CH. This is one of the OEDOMETer used for the triaxial. We can use 3 specimens at a time to get the heave prediction values. So this is another OEDOMETer. You use it for the purpose of finding the heave predictions. There is another method called Nelson et al. Method. So wherein the CH is equal to percentage of SEA log of C prime CW and C prime I of EA. And this delta H, you again use the CH value here. It's a log of sigma prime CV and sigma prime VO is a stress level. Then H is the thickness of the layer. CH is a constant from the OEDOMETER test. It is this value. Now percentage of S is the percentage of swell. The corresponding to the particular value of sigma double prime of I expressed as a percentage. So CH is an HEAVE index and sigma prime sigma V is the swelling pressure from the constant swell test. Then sigma prime V naught is the vertical stress at the midpoint of the soil layer for condition, which the HEAVE being computed. So there is a V naught is there, sigma CV is there, swelling pressure for the constant swell test is also there. So using these stress values, log value of that will be taken as a constant. Along with that, CH is the slope of the line and thickness of the swelling layer. You multiply, you get delta H, which you call it as the swell potential of the soil or the swelling value for the soil. So if you have if you change the water content, if you have an applied stress, for example, a 3.3 kilopascals you apply a load. So that is this into lines. So if you apply some load and then you change the water content, you go and increase the water content of the soil in the OEDOMETER, then the swelling will take place. Then the increase in vertical height divided by the original height of the soil specimen gives the vertical strain of the specimen. So if you increase, for example, a 20% of moisture content, you measure the strain. When there is a 25%, you measure the strain. When there is a 30%, you measure the strain. You plot it them and draw an average graph. It is a straight line graph. Now you apply another load of 8.85 kilopascals. You again plot this and get another line, the black dots. Then you increase the load to 12.5 kilopascals. Then you again increase the water content to get the vertical strain. You get another line. So when the vertical stresses goes on increases, the slope of the line go on decreases, which tells you when the vertical stress is very heavy, then automatically swelling is arrested because of the very high pressure from the other end. So if you just plot the applied stress, this is 3.3, 8.3, 12.3 on this line, and CW, the slope of this line. This is the slope for this line. This is the slope for this line. The slope means the difference between these two. The ratio of these two things is your slope. You take that slope and then plot it, you get another graph. So this graph tells you the slope of this line for an applied stress. The response of the strain to change in the water content observed in the swell test, then the relation between the slope CWE and applied stresses, we can draw the graph. Now using these two things and using the formula what is presented in the earlier slide, you can get what is the delta H there. The delta H is exactly the predicted value of your HEAVE. So if you use some of the methods, you can draw a comparative graph for the research purposes. HEAVE occurred on the test. On the test, you can get some value. What is a HEAVE occurred? And there is another test, prediction HEAVE, the Nelson et al. Method you can get. Then prediction of HEAVE, Marr et al. Method also you can get. So if you compare, they are very nearly equal. So the Marr et al. Method, actual experiment, as well as Nelson et al. Method very closely follow the experimental values. So we conclude these two methods are more reliable method to predict the HEAVE of the soil or the HEAVE potential of the soil. So that's why we are studying these two methods to find out the HEAVE potential of the soil, because they very closely follow the actualities. The comparison of the HEAVE profile throughout the depth of the soil between the predicted and measurements are shown in the figures. Now, what are the effect of the HEAVE? That is about the HEAVE. When a HEAVE takes place, what will happen to the soil? What will happen to the structure? Let us see one by one. This is about the theory of the heaving, but we should know as a soil mechanics engineer or the geotechnical engineer, what are all the implications on the foundations. Now, the odometer test gives some list of the conclusions. The advantage of the Moore-et al. Prediction method is that method can be made using only the water content data. The data resulted from the fairly routine geometrical laboratory test. Yes, you can do it. Most geotechnical engineering laboratories are well equipped with a setup and run the test. But the test procedure takes a long time, but long time means 14 to 15 days. It is not the time by 1 hour, 2 hours. It is number of days. To set up and run the shrink swell test, the test procedure need a lot of specimen that identical, and it is difficult to ascertain whether the specimen prepared are identical. So preparation of the specimen is very, very important, because to predict a swell, you have to do a series of tests, because you have to go on changes the stress level, and then you are going to find out the strains for a differential water content. So because of that, your specimen should be consistent. So when you prepare a mass of the soil, then from there you take small pieces to make the small cakes, which will be used in the OEDOMETer. The test produces needs a lot of specimen that identical, and it's difficult to ascertain whether that specimen prepared or identical. You have to assure it. The CH parameter that used in the Nelson et al. Prediction methods are more rigorous, and it's based on the consideration of both applied stress and suction as well as water content. Yes, we saw all those things. But it needs both CS and CV tests to determine the CH parameter, two values of the stresses. In routine geotechnical laboratory, only CS test is conducted, hence only CS swelling pressure is measured. One of the proposed method for determining the CH parameter was the M method as used in this study, but we are not going to the explanation of this M method, because our lecture is concentrated only about the preliminary aspects of the heaves in the soil. The heave prediction using Nelson et al. Method is influenced by the quality of the oedometer test results. The accuracy is determined the CV swelling pressures and CH parameters. So that's how you use the oedometer test and predict the heaving of the soil. Normally we do it. Now let us go to the next phase of the soil heaving activities. Soil degradation and conservations. Because of the soil is heaving, there is a movement of the soil occurs, and it has to mix with other materials surrounding it. And then it has to expose to the weather, and it has to receive dust particles and other materials carried away by the wind and water, things like that. With the result, the soil sometimes may get fertility, sometimes it loses the fertility. Most of the time it becomes degraded because of weathering. So when the soil heaves and then shrinks, you get a lot of the cracks like this, and then the soil degradation takes place. So such type you should conserve it by having the vegetations on the surface, green vegetations on the surface. So cutting greeneries are never be good for any aspects. Soil ecosystem changes through the succession. The fertile soil contains the community of organisms that work to maintain functioning nutrient cycles. These communities help to keep the soil resistant to erosion. For example, the barren rock then leaches, that is, it gets weathered and becomes smaller. The small annual plants and lichens can be grown in that, because when there is a stagnation of the water, the small plants can develop. So maybe algae, fungi, things like that. Then next stage is the grasses and perennials, which are permanently living on the structure, living on the surface of the earth. Then you go to the larger trees, intermediate species, the grasses, shrubs, shades, then intolerant trees such as pine trees, things like that. Then shade of tolerant trees, and the climax of the community starts. So the primary succession of the soil is by start from the rock, it goes for the fertile soil, but when there is a soil healing takes place, it goes back to the lichens and small annual plants, or it goes to a, eroded soil or an unused soil or not usable soil. Two main types of the process can give rise to the soil degradation. What all the two things are? The process that takes away the soil erosion, no or little vegetation soil and wind and water. They do a lot of work on the soil, work of wind, work of water, work of air. The process that makes the soil less suitable for use and loss of chemicals, nutrients, leachings, addition of chemicals, pollutions. Generally, the commercial industrialist food production systems reduce the soil fertility more than small-scale subsistence farming. So these are all some of the effects of the soil degradation because of the soil heaving. Erosion. Movement of the soil, especially the surface, litter and topsoil, two main agents of the erosion, wind and flowing water. So maybe the river, when the river meanders or when there is a scour in the river, then the soil will be eroded away and deposited again with some other soil. With the result, there may be soil fertility may be increasing, or sometimes the fertility may be decreasing. So the soil may be eroded and it becomes less fertile also. Soil erosion will become like this. So green vegetation will be spoiled here. So if any heaving of the soil is there, then such things will happen. Because of the very heavy wind, then the topsoil is being eroded away, and sometimes some useful materials and degraded material used as a fertilizer can also fly off along with that. Of course, toxification. Now the industrialization has started all over the world. So increasing soil acidity caused by leaching of the metals, burning of plant material, pH value changes, coal power, coal power plants. So the coal ash, fine handling ash, and then all those things will be mixed with soil. Soil gets degraded very, very badly. So toxification is very dangerous for the soil. Not only for the soil, for the living being also it will be very, very dangerous. Please bear in mind, toxification is never be good for any part of the earth. But you cannot live without toxification. Salination. Salination is deposits of the salt from the seawater. It deposits and then it spoils the water. It spoils the soil, because all the salt, which may be a magnesium, and other calcium carbonates are being deposited, then some amount of potassium also being deposited in the soil. They are all very bad for the living things, and they are all very bad for the foundation also. You cannot put a foundation on the salt, because that will spoil even the reinforced concrete also. So whatever is not good for us is not good for the structure also. Please have that as a general formula in your mind. So salt built up in the soil are never be good or never be accepted as a good foundation soil. Gullying is the some part with the, so you might be seeing some potholes on the roads, but it will happen in the very large diameter in the barren land. You call it as the gullying. The channel develops on the hillside, then following the rainfall, over time, they get deeper and deeper. As I was talking to you about swelling, so when there is a swelling stops and there is a shrinkage takes place, that soil may move upward, then there will be a bottom side, there will be a empty spaces being vacuum being created. That vacuum being occupied by the landslides. So when such things happens, so gullying happens like this. So when there is a landslide happens, because of the swelling soil swells abnormally and removes some of the material. When swelling soil contracts, then it replaces the soil at the more deeper level, which creates something like the gullying or the potholes. Potholes is very small magnitude, but this is a very big thing like a valley things. The effect of trees. When ground shrinks as the tree drains, ground is hot and dry and swells. So when the ground shrinks, the tree drains ground in the hot. So the trees are always keep some of the moisture content. If you cut off the trees, then ground can swell or the heave the tree is felled. Because whatever the water is being used by the soil, by the ground roots, are being not used now, with the result, then soil gets swell because of that moisture content, which causes a cracks in the building. When the soil goes up, obviously there will be some moisture content will be there in the soil. So these are all the effect of cutting of the trees, swelling of things like that. So that's how the tree sees whatever you see on the above the ground, you can see a similar root of the tree is below the ground. So whatever the size of the tree on the ground, the similar size of the tree will be growing underneath also as in the form of the roots. A tree roots run to be as deep as its branches are high, tens. For this reason, a tree can be a major cause of the subsidence. So because of the tree, the roots of the tree can cause us the swelling and then shrinking of the soil, and it contribute to the soil very much. So tree swelling, trees falling is not good for the foundations. So when there is a heaving it takes place at the bottom level, the floor will be lifted up. And suppose heaving doesn't take place these 2 points because of the concentrated load here. So the heaving takes place where the less concentrated load is there. So soil heave and bulges out and push the flooring and it develops some cracks there. You call it as the heaving of soil. So sometimes the damage can occur like this. The flooring cracks and the column gets lifted up bodily and there could be a crack on the side walls also. This you call it as the heaving failure. This is a very small type in magnitude. Their macro size of these problems can also occur like this. A very big structure can be swelled, can be heaved and then swallowed by the soil and it has to be underpinned like this. And very big structures can also fall because of the soil heaving. So the raft foundation can be tilted as such because of the soil heaving, and it is not something uncommon if you put a raft on the black cotton soil or heaving soil. So very big structure or the retaining structures can be heaved very badly, pulling down the structures. So you have to protect it with some other material to see that that heaving of soil is stopped. So when the soil heaves like this, if you allow it to heave, then the full structure will have to come down. You don't have any other choice other than that. Only thing is it may be a time scale bound or a time bound activity. So it gives enough warning for the people. The life of the people may not be lost, but structure will be lost, which is also very expensive loss. So your total structure can multiply and then multiple fracture can happen in the total structure and finally it can come down in twisted form like this. A bunker and a silos can be pulled down because of the heaved soil, and you may be thinking that soil can be loaded with bunkers to compress and keep it intact. Not necessarily like that. So differential settlement, differential heaving can cause the structure to fail like this, collapse like this. So to protect it, you have to have the cofferdam or the sheet piles have to be driven nearer to the heaved soil and then see that the soil doesn't heave further in the lateral directions. So lateral direction heaving can cause the subsidence of the structure at the different places. So if you want to avoid the lateral heaving of the soil, you develop the cofferdam and then you put that cofferdam and then you put it with some strong piles and then you cast it. Then you can retain that earth so that the heaving can be stopped. Not necessarily heaving has to be measured only on the area where you construct a building. Suppose a very big hillock or very big rock mountains are there, heaving can take place, causing the very big crust of the structures, crust of the earth formation can also heave like this, or it can heave on either side and open out, and you can see what is happening inside the heaved part of the soil. So thank you, and that is the end of our lecture. And thank for joining with me. Once again, I thank you for to join with me. So we will continue with the next lecture, maybe after few days. Thank you. Thanks for joining with me.